today we talk about Fibonacci heaps. Let's go. So, what is a Fibonacci heap? Fibonacci heap is a heap. So, it is data structure which supports operation like add element and remove minimal element. Like a normal binary heap, which we discussed on the second lecture, I think. So these two operations are the common operations for all heaps. It also supports some other different operations. It also supports two important operations. First important operation is to merge two heaps. They are merged like in disjoint sets. So you have two separate heaps, and you like unite the set of all elements. Like you have one big heap which contains all elements of both heaps. And the final operation is to decrease the key. This operation basically takes some element which is already in the heap and change the key of this element to some another key. So we take some element x and change the key to y. So what happens? We have the element in the heap somewhere. So some element x. That's a spoiler. The situation will usually look something like that. So we take this element, so we have like a pointer to this element. So we have pointer to this element x. And you change this element x with y. And you can do it only when y is less than x. Y should be less than x. So this is the operation decrease key. We take some element which is already in the heap and decrease the key of this element. That's all. That's all we want to do today. Looks not that hard, right? First, let's talk about what we already learned. We already know how to make binary heaps, right? If you use binary heap, then you can add element in log n time. You can remove minimum in log n time. You can decrease the key in log n time, just decrease the key and then sieve the element up. So you can decrease the key in log n time. You can't merge two binary heaps easily, but you actually can do it. Like, if you think about it, when you do something like we did with the disjoint sets. So if you merge two heap just by inserting all elements of the smaller heap to the bigger heap, then you will take something like log square, but it's not widely used. So most commonly, binary heap supports these three operations, and they all work in log n time. Share some code. I don't think I will write a code of Fibonacci heaps because it's not supposed to be implemented. No, I think it can be implemented pretty easy. So the code will not be hard. So, but it's just not effective enough because the constant factor will be too big. So it's not usable in most problems, but I think it can be implemented pretty easily. The code is pretty simple. We'll get to it a little bit later. Now, first, before we learn what is Fibonacci heap and how to make Fibonacci heap, we will learn some simpler heap, which is binomial heap. Binomial heap is just, it's something like Fibonacci heaps, like first step before we reach the Fibonacci heap. It's just easier to understand Fibonacci heaps when you already know how binomial heaps work. So let's go. What is binomial heap? Binomial heap is the heap which is built on top of binomial trees. So the simple heap we discussed on the second lecture is based on binary tree. So each node has exactly 2 children. And binomial tree is something different. Binomial trees looks like this. There are binomial trees of different ranks. So binomial trees of rank 0 is just one vertex. So this is the binomial tree of rank 0. Binomial tree of rank 1 is just 2 vertices. One node and another node here. Looks very simple, right? Now let's say binomial tree of rank 2. Now it gets a little bit more complicated. We have something like that and 2 more vertices here. And binomial tree of rank 3 looks like this. We have vertex and we have 1 vertex here, 2 vertices here, and another 4 vertices here. And so on. So the binomial tree of rank k looks like this. So if we have rank bk, looks like this. You have the vertex, and the root of the tree has exactly k children. The first child is just 1 vertex. Second child is 2 vertices. Then we have 3 like this. Here we have 3b2. Here we have 3b3, and so on. The last tree is bk minus 1. So we just take all the previous trees, combine them, and build 1 vertex above. This is how binomial trees are constructed. So each binomial tree, each next binomial tree constructed of all previous binomial trees combined by 1 common root. Okay. There is another way of thinking about binomial trees. Is the following. You can think of binary or binomial tree of rank k like this. So binomial tree of rank k is constructed by taking binomial tree of rank k minus 1 and adding another child here, which is also a binomial tree of rank k minus 1. So that's another way of thinking about binomial tree of rank k. So again, it is the same scheme. So here you have binomial tree of rank k minus 1. It means that you have a root and the children have ranks from 0 to k minus 2. And here you add another tree of rank k minus 1. So you have all trees from 0 to k minus 2 and another of k minus 1. So you have all trees from 0 to k minus 1. Is it clear enough? Just, you're too quiet again. Just, if everything is clear, just say everything is clear, so I will stop and go to the next. Now, that's binomial trees. Now, we need is to build heap on top of these trees. And how to build a heap from a tree? No, it's simple. You just take some tree and make the heap invariant like we did in the binary heaps. For example, we can take this tree and put the elements in each node of this tree. For example, here we may take this tree and add some elements. Let's add something. Take something like that and add some numbers here, like 1, 5, 4, 6, 8, 3, 9, 10, and 25. That's the heap which is built on top of the binomial tree. So we maintain the following property, that each element is less or equal when its children. This element is less or equal to this, less or equal to this, less or equal, less or equal. Yes. That's the plan. That's the plan. That's how we will construct our binomial heap. Now, what is if we can use only these trees, what is the number of elements we can make? So, what is the number of nodes in the binomial tree of rank k? You can see that binomial tree of rank 0 have 1 node, this has 2 nodes, this has 4 nodes, this has 8 nodes, and so on. So, the binomial tree of rank k contains exactly 2 power k nodes. Good. So, if you want to put exactly 2 power k elements in your binomial heap, that's fine. You just take the tree of rank k and build heap like this. What if the number of element is not a power of 2? For example, what if you want to put, like, say, 11 elements in your binomial heap? So if you have 11 elements and you want to build a binomial heap of these 11 elements, what can you do? You take not one tree but several trees. So you take this tree of rank k, of rank 3, and put 8 elements here. Now 3 elements left. So you take another tree of rank 1 and put another 2 elements here. Now we have 8 elements here, 2 elements here. It's 10, 1 more. So we need another tree of rank 0. So add another tree of rank 0. That's all. That's how we support the binomial heap of 11 elements. So let's add some elements here. So we have 2 and 7 here and 17 here. So that's the correct binary heap, the binomial heap of 11 elements. This is the binomial heap. It will always look like that. Again, what we want to do? We want to make several binomial trees, and the total number of elements in these trees should be n. To make it fast, we want the number of these trees to be minimal possible. How can we, what is the minimal possible number of trees we can take so that the total number of elements is n? Oh, that's quite easy. Because we cannot add elements. So we use several trees because we want only the trees of this fixed structure. We want to use only the trees like this and do not the structure of the tree is fixed. So you can just add one more element to this tree. It will be not the correct binomial tree. So we want to construct the heap only from binomial trees. So we only want to use trees like this. And because the number of elements is always 2 in power of k, then sometimes we need several trees. So if we have 11 elements, we need several trees because the size of each tree is the power of 2. So we need to split this 11 in 8 plus 2 plus 1. And put 8 elements here, 2 elements here, and 1 element here. What is the advantage is? Good question. We will have a look. The advantage is that we will be able to make all the following operations. We'll talk about the advantage of, if you compare it to the usual binary tree, then the advantage will show what the advantage is. The advantage is that you could easily merge these trees, actually. We'll talk about it just in a minute. We'll talk about the advantages in a minute. Cool. Again, what I want to do, I want to take the minimal possible number of trees. Let's say without what can be the minimal possible number of trees? The minimal most possible number of trees will be about logarithm of n. Because how can I split this n in log n summations like this? I take the biggest possible power of 2, subtract it from n. I will get a number at least twice less than n. Then I take another biggest possible power of 2, subtract it from n, and so on. So the number of trees, if each time I take the maximal possible power of 2, then there are two consequences. First, all ranks of this tree will be different. No, because if I take 2 trees of the same rank, it means that I can take the one tree of the next rank instead. So if, for example, I take 2 trees of rank 1, it means I take 2 vertices plus another 2 vertices. Instead of this, I can take just this tree. So the total number of trees will be less. So if I take the minimal possible number of trees, then all trees must have the different rank. And the second consequence is that all ranks are not more than logarithm of n. All ranks are not more than logarithm of n. It means that the number of trees is at most log n. Is it clear enough? Again, why all ranks are different? Because if you have 2 trees of the same rank, it means that you use like 2 vertices and another 2 vertices. Instead of doing this, you can take just 1 tree of rank k plus 1 and put this vertex in this bigger tray. So if you want to minimize the total number of trees, you always keep all ranks of all trees different. And the second is, because all ranks are at most log n, because tree of rank k contains 2 in power of k elements, this k shouldn't be more than logarithm of n. And if all ranks are different, and ranks are no more than logarithm, then the number of trees is at most logarithm. Cool. That's all. That's the binomial heap. Now, let's implement all operations. all operations in binomial heap work in log n time. So I will just implement all these operations in log n time. Let's start from the first operation. Let's add one more element to the binomial heap. How to add one more element? Well, let's just add one element right here. Right here. So suppose you have one more element. You want to add it to the binomial heap. Let's say element 4. So this is element 4, and I want to add this element to this binomial heap. First, one element is the binomial tree of rank 0. So let's just think about this one element as a small tree of rank 0, like this. So this is tree of rank 0. Let's try to add this tree of rank 0 to our binomial heap. If in our binomial heap there is no tree of rank 0, then we just add this one more element to the binomial heap, like one individual tree. And it's done. And if we have the tree of rank 1, then what can we do? We can merge these two trees. So again, we have this tree of rank 1. We look on this minimal tree in our binomial heap. If it also have the rank 1, then we merge these two trees in one big tree. So how to merge these two trees in one big tree of rank 1? We look on the roots of these trees, take the minimal root, and put another root as a child of this root. So we take this 17, remove it from here, and add it as a child of this 4. Now we have the tree of rank 1. So this is the tree viewer. Like this. Now we do the same. We try to add this tree in our binary heap. If we already have the tree of rank 1, like this, then what can we do? We can merge these two trees. So we can take our tree, take this tree, and combine them to make the tree of rank 2. How to combine these trees? We look on these two root elements, get the smallest element, this 2, and put another tree as the child of this root element. So we take this 4 and add it here. And now we have the tree of rank 2. We check if we have another tree of rank 2. We don't have another tree of rank 2. This tree have rank 2, and this tree have rank 3. Now all the trees have different ranks. So we have the correct binary heap, well, binomial heap. That's all. That's how you add element to the binomial heap. Again, you add element as a tree of rank 0. If you already have tree of rank 0, then you combine these trees and like fuse them together and get the tree of rank 1. If you have another tree of rank 1, you combine them and make a tree of rank 2, and so on, until you have the tree which is unique. If you don't have another tree of the same rank, then you just put this tree in your binomial heap, and you have the correct binomial heap. That's all. Again, if everything is clear, just say everything is clear. I will repeat everything until you say something. Yes, we'll get to merging in a minute. Yeah. What is the time complexity? I will show the time complexity and then we will go to merging. What is the time complexity? How can we combine two trees into one? So let's see. So if you have two trees of rank k, so we have one tree of rank k, another tree of rank k, and you want to merge them into one tree of rank k plus 1. I claim that I can do this in constant time. So how to merge two trees into one big tree? It's quite simple. You look on the root elements. So you take these two root elements, say x and y, check which root is smaller, for example, if x is less than y. Then you take the smallest root and add another child to x. If you want to be able to do this in constant time, you need some data structure which contains the children of each node in such a way that it's easier to add one more element to this list of children. And the most easy way to do this is just use linked lists, like we did here. So what you can do is to maintain your children as a linked list. I'll write right here. So you support linked list like this. I'll make bidirectional lists. That's fine. Yeah, that's fine. And you make the link. Yes, if you want to add the element to the end of this list, you need the link to the end. And you need the link something like let's have a link to both first and last element. I'm not sure which one something like that. And the same way here. So to maintain the list of the children, you just make the linked list. So you make linked list of all children here. You make the linked list of all children here. And here you have only one child. Let's have 2 pointers. So that's how you maintain the structure of your tree. So in each node, you have the linked list of its children. You have just like you have the pointer to the first element, to the last element of this list, and let's say you have the bidirectional linked list here. I think some pointers may be removed, but I'm not sure which one, so I just stay all of them. I think it's enough to have pointer to the last element and pointer to the previous element in the list. So yeah, it's good enough. It's this theoretical lecture. If you want to implement this, I think you can remove some pointers that are not used, but good enough. No, we will not implement Fibonacci heaps today. I think by the end of this lecture, it should be clear enough how to implement Fibonacci heaps. But it's not hard to implement this. It's just not you don't need to implement Fibonacci heaps because they are slower than usual heaps, usually, in most problems. What I was talking about? So if you maintain your trees like this, then you can add this y to this tree in constant time. So if you want to add this element here, you just have this pointer from x. So you have pointers to the first and the last element of this list. So you just take this last element. Do you see it? You take the pointer to this last element, add this y to this list, and move this pointer here. So you do it in constant number of pointer machine operations. So the total number of operations here is constant. Now let's look how we add element. When we add one element to the binomial heap, then we add element as a tree of rank 0. Then each time we combine two trees, and get the tree of the bigger rank. So first we add one tree of rank 0, then we combine and get the tree of rank 1, then we combine, get the tree of rank 2, and so on. So each time we combine two trees, we increase the rank of the current tree. And all ranks are not greater than logarithm, so total number of these merging two trees will be at most logarithm. So the total time complexity of this add operation is log n. So all operations will be in log n time. Okay, that's how you add one more element to the binomial heap in log n time. Good. Let's go next. Let's talk about merging. Merging two binomial heaps is actually quite the same as adding one more element. So actually, adding one more element is actually merging one heap with the heap of single element. So I need to clear something. Let's clear this. I don't need this anymore actually. Let's talk about merging. How to merge? How to merge two binomial heaps? Pretty much the same like we did when we merged two sorted arrays. So you maintain each binomial heap as the list of trees, and you keep this list in sorted orders by the ranks of the tree. For example, let's say we have one tree of rank, again, we have of 11 elements, like here. So we have tree of rank 3, like this. Another tree of rank 1, and another tree of rank 0. Imagine we have three like this. And we have another heap, this is one. And we have another heap, let's say we have tree of rank 2, tree of rank 1, and another tree of rank 0. Like this. This is heap 2. And we want to merge these two trees into one big tree. Or these two heaps into one big heap. So we do it pretty much the same as we did when we merged two sorted arrays. So each time you take two minimal elements. So we take two trees of minimal size. So you take this tree and this tree. Take the minimal of these trees and put this tree in the resulting tree, in the resulting binary heap. Here we have the tree of rank 0, and here we have another tree of rank 0. We don't want to have two trees of the same rank in the resulting binomial heap. So what can we do? We can just combine these trees into one big tree. So we take these two trees of rank 0, remove them from their heaps, then merge them into one tree of rank 1, and put this tree of rank 1 in the result. Of rank 1, of rank 1, 1, 1, 1, 1, 1, 1, 1. Again, we have these two pointers to the minimal tree in each binomial heap. So we take these two elements, two trees, check if the rank is the same, then we want to combine this tree into one tree of rank 1 and put this tree of rank 1 in the resulting binomial heap. And so on. Then we move to the next. Here we have tree of rank 1, here we have tree of rank 1. The interesting fact that here we have another tree of rank 1. So we may have three trees of the same rank at some point. So we may have one tree here, and another tree here, and these three trees will have the same ranks. This may happen. So what we do when we have three trees of the same rank? We combine these two into one tree of rank 2 and leave this tree here. So we take these two trees, again remove them, combine them into tree of rank 2, and that's all. Now in the resulting heap, all the trees have the different ranks. That's what we try to achieve. Now let's move to the next. We have tree here. Now here we have trees of different ranks. So we take the minimum size tree and try to put it in our resulting binomial heap. Now we see that these three have the same rank as these three. Now, these two trees have the same rank. We don't want to have the trees of the same rank. So when we see two trees of the same rank, we just merge them. So we take this tree, merge them together, and get the tree of rank 3. And that's almost all. Now we take this tree, look in this tree, have the trees of the same rank. So we remove this, merge them together, have the tree of rank 4. That's all. In the end, you have this binomial heap. Here, all trees have different ranks, and it contains all the elements from both these heaps. That's all. That's how you merge two binomial heaps. Actually, the code is quite easy. If you want to implement this, it's quite easy. It's basically the same as the code of merging two arrays, but a little bit more complicated. But here, sometimes when you actually you can do it the same way as you do merging two arrays. You can just merge these two arrays into one big array and then do all the merging of these trees of equal size. You can do it in this way. So you can merge these two lists into one big list with some trees of equal rank, and then in another step you just iterate over all trees, and if you see two trees of the same rank, you just merge them. You can do it like this. That's also possible. It's as you wish. That's all. That's how you merge two binomial heaps. What is the time complexity? Again, like in merging sorting arrays. Here we make a linear number of operations. When you merge two arrays, you have a linear number of operations. Each time you take either one element from here or one element from here. So total number of these operations will be linear. And total number of merging two trees will be linear, because we have linear here, so total will be linear. So it's linear from the number of trees. Yeah? So number of trees in both heaps is at most logarithm of n. So this time complexity is linear from this number of trees. So it's logarithmic. Yeah. I think it's clear enough, right? So the time complexity of this merging is log. Cool. That's almost all. Now, how to remove the minimal element? So imagine you want to remove the minimal element from your binary heap. Let's use this binary heap, binomial heap. So imagine you use this binomial heap, and you want to remove the minimal element. Well, first, let's find the minimal element. Minimal element is here. Now, let's remove this element. So we take this element and remove it from the binomial heap. What will be left? We will need to take care of its children. So after we remove this element, we have these children elements, and we need to do something about it. So what can we do? We can take all the children of this removed minimal element. Yes, minimal element is always the root of the sum tree. It's quite obvious, yeah? Right? So minimal element is always the root of some tree. Is it obvious? I think it is. So we remove this root of this tree. So we take the children of this removed element. And now we try to put these elements back in the binomial heap. How can we do it? It's quite easy. So we take this element, these children of this removed root are the binomial trees of different ranks, because all I already read this. So all children of the root elements are binomial trees of different ranks, just by definition of binomial trees. So these trees are all binomial trees of different ranks. So we can combine them in one binomial heap. We can say that this is binomial heap H2, and this is binomial heap H1. And then we just call the merge operation to combine what gets left of the binomial heap after we remove this minimal element, and this heap containing of children of the removed element. That's all. We just combine these two heaps using this merge procedure. And we get the heap which contains all the elements except this one removed element. Yeah, that's all. That's how you remove the minimal element. In the end, you need to find another minimum. Yes. After you merge these two heaps into one, you need to find the next minimal element. This can be done just, minimal element is the root of some tree. So you just iterate over all roots. There are at most logarithm number of roots. So you just iterate over all logarithm roots and find the new minimal element. That's all. That's how you remove the Cool. That's almost all. Do we need to talk about decrease key? No, let's talk about decrease. Decrease key is not that interesting in binomial heap. In binomial heap, when you decrease the key, you can just do the same as we did in the binary heap. Just decrease the key and shift it up. If you want to do it in logarithm time, the height of the tree is at most logarithm. So you can do it in the same way as we did in the binary heap. So you decrease the key and then shift the element up to the root. It will take logarithm number of operations. So decrease key is not very interesting here. That's how binomial heaps are working. Whew. That's half a lecture. Cool. Now we'll move to the Fibonacci heaps, finally. The plan is to do basically the same, but slightly harder. So we will try to improve everything to make it even faster. What is the plan? Let's go to the plan. So what is the plan? The plan is to have some operations work faster than logarithm time, actually work in constant time. First of all, we want to have add operation working constant. Actually, in binomial heaps, addition already works in constant time. We'll discuss it in the practice next week. But it is actually already satisfied. We just didn't talk about this. Now, we want to be able to merge two heaps in constant time. That's something less trivial, but it's possible. We can merge two Fibonacci heaps in constant time. Just take one heap, take another heap, boom, you have a big heap in constant time. Perfect data structure. And finally, we want to have decrease key. Decrease key also work in constant time. That's kind of strange why I care so much about decrease key operation. It's actually quite important. In some problems, which we will discuss next year, when we will discuss Dijkstra algorithm, prim algorithm, and stuff like this, in some graph algorithms, sometimes you need operation like this. So Basically, it happens in situations like this. So you have some groups of elements. Like in Dijkstra, you have like the set of edges for each vertex. You have set of edges. Doesn't matter. We'll discuss next year. It's just a teaser. So you have groups of elements, and for each element, you have the minimal element. You have minimum in each group. And in what you want to do in Dijkstra, for example, is to take the minimal group, so group which contains the minimal possible element, and take this group and remove it completely from the heap. So you want to take this group and remove all the group from the heap. And the way you do this is just by maintaining each group as the single element in the heap. So why do you need decrease key? Because when you add more elements in your heap, you add one element to this group, the minimum is always decreasing. So if you have some set and you add more elements to this set, the minimum is only decreasing. So the operation you need in the Dijkstra, for example, is to decrease the current key of the element. So you have some group in your binary heap, in your Fibonacci heap, and you want to update this group. And when you update the group, the minimum is always decreasing. So you need operation decrease key. You never want to increase the key. You only need to decrease the key. We'll discuss it next year. So it's important in some important problems of graph theory. Yeah, that's a good point. This complexity is not exactly constant. This complexity is amortized. So all these complexities are amortized. Now we already discussed what is the amortized cost. Amortized cost means that if you have some number of operations, then the sum of time complexities of all these operations will be no more than, and so on. It's not the worst case, not the best case. It's the worst case amortized time. No, we always talk about worst case operations. It's the worst case amortized time. And finally, this remove minimum. Unfortunately, we cannot make all operations in logarithm time. That's quite obvious, but it's unfortunate, but it was what expected. So this final operation will work in log n time. So we need at least one operation to work in log n time, obviously. No, amortized mean, again, you can rewatch lecture about amortized time. Amortized time means that if you have this series of operations, then the sum of times of these operations will be no more than the sum of this amortized cost. Sorry, I don't have much time to discuss amortized cost today. We have much stuff to do. You can rewatch the lecture. We have a nice lecture about amortized cost and stuff like this. So let's go. I think it will be quite clear what I mean about amortized cost very soon. Exercises. Let's go. Let's start from the simple operations. Let's start from adding one more element to the Fibonacci heap. So imagine you have standard binomial heap. Imagine you have a heap like this. Last time we tried to make the minimal possible number of trees. So we say that all trees in our binomial heap have different ranks. let's remove this property. Let's say it's okay to have trees of the same rank. It's fine. So we may have this tree of rank 2, a tree of rank 0, another tree, another tree, and so on. Let's say that that is a nice heap. Yeah. So if you remove the property that all the trees must have different ranks, then how to add one more element to this tree? Very simple. You just create one tree of rank 0 and add this tree to your binary to your Fibonacci heap. That's all. That's how you add one more element to your Fibonacci heaps. Yeah. Very simple data structure. Cool. Now, how to merge two Fibonacci heaps? How to merge two Fibonacci heaps? Imagine you have two different Fibonacci heaps. Like one Fibonacci heap and another Fibonacci heap. Again, if you don't want all the trees have different ranks, then you can just concatenate these two lists. So if you maintain each Fibonacci heap as the linked list of all these trees, then you can just concatenate these two lists. That's all. That's how you merge two Fibonacci heaps in constant time. Isn't that cool? And now finally we need to pay for this because this all was very interesting, very cool, but at some point we will need to pay. When we need to pay? When we need to remove the minimal element. So what happens when you remove the minimal element? First, how to find the minimal element? Let's have a point of the minimal element. So let's have a point of the minimal element. So each time we have a point of the minimal element, when you add one more element, you just check if this element is less than minimum, then update the minimum. When you merge two heaps, you have minimal element here, minimal element here. You check which of these two elements is minimal, and then say this element is minimal. So each time you have the point of the minimal element in your Fibonacci heap. That's simple. So when you need to remove minimal element, what do you do? So we have this. Let's have some big tree. Something here, something here. So imagine you have this. This element is minimum, and you have some other trees here and so on. So this is the minimal element. Yes, that's true. If you add elements one by one, then you will have the array of elements of rank 1. That's absolutely true. If you just add n elements one by one, you will have the list of single elements. That's true. But we will think about it later. The idea behind all this amortized data structure is something like this. If you need to do something, do it when you need it. So at some point we will need to do something. So we will just shift this time to the point when we need it. Let's just in a minute. So here, what happens when you remove the minimal element? So this is the minimal element. You remove it from your Fibonacci heaps. You remove this element from the Fibonacci heaps. What you have left? You have left all its children. Yeah. So what you can do is just add all these children to the Fibonacci heaps as single trees. So you take all these elements and add them here one by one. So just add all these elements here. Again, how to remove the minimal element? We have the link to the minimal element. We take this minimal element. Now take all its children. All children are good trees. So we take all these children and move them to this root. Now we have some more trees in our Fibonacci heaps, but it's fine. Now, where is the problem? I can do this all pretty fast. I can just take all these children, remove them, add them to the Fibonacci heaps. I can do it in constant time, basically. If I maintain the list of children as a linked list, I can just concatenate these two lists and do it in constant time. But where's the problem? Yes, at some point we need to make a good tree. Yes, that's true. But why do we need it? Looks like we are fine. We can merge, we can add, we can remove minimal element. Oh, the problem is pretty simple. After you remove the minimal element, you need to find the next minimal element. Yeah? Because we had link to this minimal element, we remove it. Now we need to have a link to the next minimal element. And how to find minimal element in this mess? It's not that easy. Because if you add elements one by one, then in the end, yeah, right, you have the array of elements. And you cannot find the next minimum fast. To find the next minimum, you need to check all the roots of all the trees. And you may have up to n trees at this point. So this is not, you just cannot do it fast. What we'll do? We will try to, again, we need to spend some time to find the next minimal element. Let's try to use this time to Yes, right. So what I was talking about? I forgot what I was talking about. Yeah, so we need to spend some time to find the next minimal element. And let's try to use this time to do something valuable. So let's try to use this time to modify our Fibonacci heap to make it more balanced. That's the idea. What we'll do? Imagine you remove this minimal element, take these elements, put them here, and so on. So in the end, you have some Fibonacci heap which is not balanced at all. So you have, after you remove the minimal element and so on, you end up with something like this. So you have some strange Fibonacci heap where is very unbalanced. One more, and another element here, and so on. Imagine you end up with something like this. So this is your Fibonacci heap at this point. And you need to find the minimal element. What you do? You just iterate for all roots of all trees. And at the same time, try to balance it. How to balance Fibonacci heaps? Very easily. Let's create an array of log n elements. And try to merge the trees of the same rank, like before. So what we try to do is to iterate all roots, and at the same time make all trees have different ranks. So we go from left to right and just maintain for each rank, maintain the pointer to the tree of this rank. So we start from here. So here we have tree of rank 1. So we put the pointer from here to this tree. Now we have the tree of rank 2. So we take the pointer from here to this tree. So it's pointer to there. Now we have another tree of rank 1. Now we check. We already have a tree of rank 1. Huh? That's not good. We may merge these two trees. So let's merge these two trees. Let's take this tree. Let's take another tree of rank 1. Merge them together. Merge them together like this. And get the tree of rank 2. Now we take this tree of rank 2 and try to add this tree of... we remove this. Oh. Now we take this tree of rank 2 and try to add it in our array. But we already have tree of rank 2. So we merge them together. And have the tree of rank 3. Yeah, it's kind of lazy restructuring. So it's like you have bad data structure, but when you need it to be good, you just only at the point when you need it to be good, you make this restructuring. Yeah. And so on. Now you go to the next element. So here we have tree of rank 3. Now here we have tree of rank 0. Here we have another tree of rank 0. You combine them. Make a tree of rank 1. Yeah. Now we have another tree of rank 1. You combine them. Boom, 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 boom. Have a tree of rank 2. And that's all. So in the end of this cleanup, you have all the trees have different ranks. That's all. So again, how you remove the minimal element? First, you take the minimal element, take all its children, add them to your Fibonacci heaps. Now you have a big number of trees in your Fibonacci heaps. You make this cleanup procedure, just go from iterate all your rows of all the trees and try to make them all have different ranks. If you have two trees of the same rank, you combine them, have tree of one more rank, and so on. In the end, you end up with something like this. This is the end state of your Fibonacci heaps after this cleanup. In this tree, you have no more than log n trees. Here you have no more than log n trees. So you just can iterate all the roots and find the minimum. Just naively, just iterate all roots and find the next minimum element. Okay, now what is the time complexity of this cleanup? Let's see. If you have, let's try. So in the end, you have three like this one. So imagine you have m trees in your Fibonacci heaps. This is before. So what happens after you clean up all the trees and make all trees have different ranks? You'll have some small number of trees. You will have log n trees in your Fibonacci heaps. So what we need to do to prove that the amortized cost is small, we need to find some potential function which is decreased when we go from here to here. Let's remember what is the amortized cost. Amortized cost is the sum of cost plus change of the potential. So this is the real time of this operation. In our case, it is m. Yeah? We just need to iterate of all trees in our Fibonacci heap. And so if we want this amortized cost to be log n, we need to have a potential function which is about minus m. Yeah, just to compensate this m. So we need to choose the potential function in such a way that it is decreased when we go from this state to this state. Any ideas? Again, how the amortized cost works? We make some potential function like this phi. And when we increase the potential function, we think that we spend more time. And when we decrease the potential function, we say that we spend less time. So when we have some long operation, we want this potential to decrease, at least by the same value as the extra time we spent. So here we spend extra m time, and we don't want the time complexity to be m. So we need to have the potential such that the change of the potential from this state to this state is about minus m, just to compensate this plus m. Any ideas about number of trees? Right. Find that. So the potential function in this case is just the number of trees in your Fibonacci heaps. Good. So what is the change of potential from this state to this state? Here we have m trees, here we have log n trees. So change of potential is log n minus m. So this delta phi is log n minus m. So the amortized cost will be m plus this change. So amortized cost will be log n. That's all. Yes, and all other operations do not increase potential. No, when you add one more element, you add one more tree. So here delta phi. Here delta phi is 1. And when you merge trees, you just don't increase the number of trees. So here, that's all. That's all. This is why the amortized cost of the remove mean is logarithm. Cool, cool, cool. That's all. That's how you remove mean. Whew. Good. Is it clear by now? Oh, cool. That's all. That's how you remove the elements from the Fibonacci heaps. And now, finally, the final step. We need to make this operation decrease key in constant time. Unfortunately, this is the most hard step in this. So I need some room to make this. Whew. We're close. We're very close. Whew. Come. What happens when you decrease the key? Unfortunately, many bad things may happen when you decrease the key of the element. So if you have some element in your tree, somewhere inside your tree, so it has some parent, it has some children. So if you decrease the key of this element, it eventually may be less than its parent. And you need to do something about this. You cannot just shift the element up because it will be shifted up to the root and it costs logarithm time. And you want to make it in constant time. So you want to do something fast, but efficient. Unfortunately, you cannot do it when binomial trees. Binomial trees have very fixed structure. So every binomial heap of rank k always look like this. So the structure of binomial tree is always the same. So it's not flexible enough. So to make decrease key working fast, we will introduce another tree. So instead of binomial trees, we will use another type of tree. Yeah, but basically, a binomial tree is not very useful because it is always the same. You cannot just remove something. You cannot add something. It's always the same. You two times. So you need something more flexible. And let's talk about the trees. We'll use different type of trees. The trees will look like this. So what happens when you have a binomial tree? If you have binomial tree of rank k, let's remember one more time. You have k children, and children have ranks 0, 1, 2, and so on, k minus 1. Oh, it was converse coders. Sorry about that. We have a schedule. Sorry. So what we will change? We will change these ranks. So now again, all trees will have ranks. So if you have tree of rank k, so instead of using these trees, we'll use different trees. If you have tree of rank k, it will have k children as before. But what will be the ranks of these children? It's a little bit different. So the first child must have rank at least 0. That's quite obvious. All ranks are at least 0, but it's the next child should have rank at least 1. Next child rank at least 2, and so on. The last child have rank at least k minus 1. So now we have all ranks not equal to this, but at least this. That's the first change. What's your method button? Let's talk about I remember this. I'll talk about later. I'll explain this method and then we will move to your method. Okay. Sorry, I just have not so much time left. Sorry. Again, we move from this tree to this tree. This is much more flexible tree. Yeah. Here you don't have to move exactly these trees in these positions. You can move some bigger tree in this position and so on. And the next improvement is that we will allow the tree to lose at most one child. So we'll have tree of rank k like this, and we will have tree of rank, let's say, k with asterisks like this. And this is the tree of rank k which lost one of its children. So instead of having k children, it has k minus 1 children. And these children have ranks at least 0, at least 1, and so on, at least k minus 2. Yes, two children may have the same rank, yes. Ranks of the children may be the same. We will draw the nice trick here. Interesting question. Imagine you have two trees. One tree is the tree of rank 2, And another tree is tree of rank 3 with one child removed. What is the difference between these trees? So in this tree, you have two children. Left child has rank at least 0, this at least 1. And if you have tree of rank 3 with asterisk, then you have the same. It means you had 3 children and then you lose one of them. Yeah. So again, you have 2 children. Left child have rank at least 0. This one has at least 1. So what's the difference? Why do I make these two types of trees, like these trees and these trees? What is there any difference between these two trees when you use them in your in the big tree? It turns out that this difference. What is the difference? Imagine you have tree of rank 4. So the tree of rank 4 have 4 children. Let's look on the rightmost child. On this child. This rightmost child must have rank at least 3. So this tree have rank 3. So we can put this tree in this position. But this tree have rank 2. It is the same as this, but the rank is 2. Yeah. So we cannot put this tree in this position. That's the difference. So why do we care about this? Because it will help us to make the amortized cost equal to constant. Yeah. We will maintain these marks, and it will help us to make the amortized cost here equal to constant. No, we remove the entire subtree. Yes, yes. Yes, this tree is lost one child with the whole subtree. Yes. So one subtree of this tree is absent. Yeah. Well, for example, let's move here. So here you may have tree of rank 3 are here, and you have here you have rank 0. Here you may have 1 little six. It is the same as 0. Here you might have something like 2. So you have 2 children here and 2 children here. And here you might have like 1, why not? So leftmost child must have rank at least 0, but 1 is at least 0. So we may have two children of rank 1, why not? We may have one here and 1 at asterisk here, so we may have rank 2 here actually. Okay. That's the perfectly normal Fibonacci tree. Yeah. It looks kind of more funny than standard binomial trees. So standard binomial trees are very boring. These trees looks cool. So what we have here you have 0, here you have 1. So this is the correct Fibonacci tree. We will use trees like this. Isn't it cool? The only property we need from these trees is that the rank of ranks in this tree must be at most logarithm. Now, when we have a tree of rank k and remove one child, we get the tree of rank k but with one child removed. So this mark shows that we removed one child from this tree. We can remove at most one child from each tree. So we have this tree of rank k is just a normal tree of rank k. So it has k children with these ranks. And this tree is tree of rank k with one child removed. So it's different. It looks the same. Again, these two trees looks exactly the same, but these ranks are different. And we maintain these ranks, and it will help us to make this time complexity constant. Good enough. So when you remove one child from the tree of rank 3, you get tree of rank 3 with asterisk. It's not the same as tree of rank 2, because you cannot put tree of rank 2 here. But you can put tree of rank 3 here. Why not? We may have just before. Why not? Here we have node of rank 1. The node of rank 1 must have one child, and this rank should be at least 0. 2 is at least 0. So it's okay to put a tree of rank 2 beneath the node of rank 1. That's fine. I'm not sure if we ever will get some. No, we may end up with situations like this. That's perfectly normal. Yeah. So we can put the tree of the bigger rank to the parent of the small rank. That's fine. No. Rank is not. No. Here, rank is not the. Yes. In the previous lecture, we have ranks equal to the length to the deepest leaf. It's not the same here. Here, ranks are just different numbers assigned to each nodes. It's not connected to the depth of the tree. Yeah, no. Not like before. They all called ranks in different data structures, but they have different meanings usually. So these ranks are different. So here, the rank is basically the number of children. Or -1 sometimes. Cool. So we just assign some numbers to these nodes and maintain this property. Oh, finally. Let's go back. I will not prove this. Leave it to you as an exercise. So if you have tree like this, the rank of the root will be no more than c multiplied by log n, or some constant. You just prove this, it's not hard. You just check what is the minimal number of elements in the tree of rank k, and then make logarithm and so on. So it's not hard. Leave it for you. Let's go here. How to decrease the key? How to decrease the key of L? Just by definition, this mark shows that we removed one element from this subtree. We allowed to remove at most one child of any node. So any node of rank k has k children or k minus 1 children. If it has k minus 1 children, it means we removed one child, and we have this mark. So this mark shows that we removed one child. Just by definition, we allow this, and even when we're allowed to remove one child, the ranks will be up to logarithm. That's the interesting part. So even when we allow to remove one child from each node, the ranks will be up to logarithm. it will not be the same as before. So before it was just logarithm base 2. Here it will be something different, some little bit bigger, but small enough. Some logarithm. Finally, let's go. So how to decrease the key of the element? So you have the element x, and you want to decrease its key. It has some subtree here and so on. So what do you do? What do you do? You take this tree, decrease the key, and then this condition may be broken. So if this condition breaks, you just take your tree and move it to the root. You just remove x from its parent and move it to the root. So here you have the list of your. So this all happens inside some of the trees. Here we have some other trees. This is your heap. So inside one of the trees of your Fibonacci heaps, you try to decrease the key of this element. So you decrease the key of this element. This condition broke. So you take this subtree, detach it from its parent, and move it as a separate tree to your root. That's all. Now, when you removed the child from this element, you need to put the mark here. So you put the mark here so that you removed the element from this node. But it may happen that you already removed one child from this node. So it may happen that when you remove the x from this parent, you already have this mark here. It means that you removed 2 children from this node. Yeah. So this mark shows that you remove one element from this node, and now you remove the second element from this node. That's not good. We don't allow to remove 2 children from the same node. So when this happens, this tree is kind of invalid. So it was tree of rank k with 2 leaves removed, 2 children removed. So what we do, we just take this tree, and detach it from its parent. Remove this, and move this A to the root list as well. So we put this. And so on. And now we go up to the tree until we reach some vertex which has no mark. So yeah, we have the vertex x, decrease the key, detach it from parent, move it here. Then go to the parent. If the parent have this mark, it means that we remove 2 children from this leaf. So we detach it from the parent and move here. And we do it until we reach some point. So we have a mark here. Let's let be. So we go here, we have a mark here, we detach it, move it here. Move here, detach it, move here. Detach this, move B here. And in the end, we will go to some vertex which has no mark. It means that we didn't remove anything from this vertex by now. So we put the mark here. So we put the mark here, and that's all. That's all. That's how you decrease the key of the element. You take the element, remove it from its parent children list, move it to as a separate tree to the root list. Go to the parent. If the parent has mark, then we detach it from its parent, move it here. Then also and so on. That's all. That's all. Now, when you move the element to the root list, you can remove this mark from this list. Because you only need these marks when you attach this element to some another element, just to satisfy this condition. Yeah. And if the element is the root of the tree, you don't need this. So, for example, if this tree A has rank k, so it was k this answer. So if it has rank k, this mark, it means that now it has k minus 1 children. Then we remove one more child. It means now it has k minus 2 children. So when we move it to this root list, we just remove this mark and say that it is a normal tree of rank k minus 2. That's all. So we moved all these vertices to the root list and remove these marks. Good. Now, finally, let's calculate the time complexity. What is the time complexity? What we did? Imagine we walked, let's say we have k vertices. So imagine we have k parents with marks. So we start from here, go here, 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 detach everything, move it here. What is the time complexity? So again, amortized time is time plus delta phi. So what is the time here? Time is simply something like k plus 1. So we move from here, we make like k plus 1 operations just to go here and to detach everything and put it here. So we need to change our potential function in such a way that when this happens, this potential should be decreased by something like k. It's quite easy. So what we need to do, what is decreasing when we make this operation? Decreasing is the number of nodes which have these marks. So let's say that potential is the number k can be, yes, can be up to n. Yes, we may have a single chain of nodes. So k may be up to n. It's normal. The good thing is that if k is big, the potential function must be decreased by n. If potential function will be decreased at the same time, then the amortized time will be good. Yes, time complexity, this real time complexity will be n, but the amortized time complexity will be constant in just a second. So again, how to make a good potential function? We need to look on the long operation and see what is decreasing when we make a long operation. In this case, the number of nodes which have these marks is decreasing because we move these nodes to the root list and remove these marks. Let's say, so we have, before to get this complexity, we need to have a potential equal to the number of trees. Now it's something we also, when we move these elements to the root list, we increase the number of trees. And we need this number of trees to make this time complexity good. So let's do the following. Let's say that the time complexity, or let's say that the potential is the number of trees plus 2 multiplied by the number of marked nodes. Yes, the idea that we need to maintain the same potential function for all operations in your data structure. That's good to go. You need to have some potential function which is good enough to maintain all the amortized cost of all your operations. Yeah. So we need to have. I need to have this number of trees in order to have this time complexity good. Yeah. So I just add to this number of trees 2 multiplied by the number of marked nodes. Then what happens to change of potential here? So how potential is changed? I remove these marks, so it is decreased by 2 multiplied by k. Now I move these nodes to here, so I have k plus 1 new nodes here, so it's plus k plus 1. Well, that's different lines. So I removed marks from here. I moved these nodes here, so plus k plus 1. And also I add one more mark here, so it's plus 2. So the total change of potential is minus k plus 3 minus k. That's all. Now we just add this and this and see here. That's all. That's how you decrease the key in the Fibonacci. Okay, again, the idea is pretty trivial. So we just allow each node to lose one of the children. And now when we change something, we just detach this element from its parent and move it to the root. Each time we do this, we remove this one mark and move this element to here. So here we have plus 1 potential, here we have minus 2 potential. So each operation is decreasing your potential. So you move to the root, and each operation is have delta phi minus 1 and TL1. So these all operations are free. You may think about this in the accounting method. So you can say that each mark have a coin of value 2, and each root have coin of value 1. So like you have 2 coins here and 1 coin here. So each time you go to this, you have 2 coins. You spend 1 coin to move element here and put 1 coin here. So each time you have. And here you go to here and put 2 coins here for future. So each time you have this bad element which lost one of its children, you just reserve 2 coins for future. And in the future, when you go to this element, when you fix this, you get these 2 coins and to fix something like that. Okay, hope it's clear enough. Okay, it was the hardest topic of this semester, I think, but hope it was clear enough. So again, thank you for joining me. Let's answer your questions.